Hello, students of geometry. Welcome to 11.3 volumes of pyramids and cones. We're going to take a look at both of those shapes here in this lesson. The proof for these formulas goes a bit beyond just your standard geometry class, so feel free to Google that if you really are interested why the proof or why this formula works the way it does. But the formula itself is pretty straightforward to use. It's very similar to the volume formula for prisms and cylinders, except it has a 1/3 in front. If I were doing a demonstration, or I have done demonstrations in class in the past, I would probably do that again if we were meeting. But I have a three-dimensional hollowed out pyramid that has and then I'm going to do this here. So this is the height from there to there. It has a hollowed out pyramid. I fill it up with water 3 times and I pour it into a rectangular prism that has the same base and height, and it works exactly. Like the surface tension of the water is just perfectly at the top when I do that demonstration, or when I've done that demonstration in the past in class. So kind of a cool experiment, but the first time I saw these formulas proven and I really understood them was at the pre-calculus calculus level. So I just need a little more background, I feel like, to understand the proof behind that. So hopefully you'll get there mathematically someday and we'll be able to understand the proof behind these formulas. A cone is really just a pyramid with a circular base, or a polygonal base in a sense of infinite sides. So the formula is the same, just as it was for surface area, comparing that surface area of cones to pyramids. Very, very similar, essentially the same formula. But again, just like it was for a cylinder compared to a prism, a cone compared to a pyramid, the base is always going to be just pi r squared. So I can replace b with pi r squared and have that in its place. So the height would be the perpendicular height here, and you got capital B there. The radius would be from the center of the circle to any point on the circle there. So let's take a look at cones. We're going to start with the second one here again, and then look at some pyramids after that. So the volume of a cone, 1/3 pi r squared h, will be the formula we'll use for that. This one didn't quite give it to you directly. I gave you the slant height here. Remember, we refer to that with a cursive L. So this is my h here. So I would say h squared plus 5 squared equals, and I'm going to replace L with 13 squared. And so I'd have h squared plus 25 equals 169. You could subtract 25 from both sides and get 144. And then you could take the square root of both sides to get h equals 12. So the height is exactly 12. That's a Pythagorean triple, 5, 12, and 13. And your radius, plug it in as 5. Your height now is 12. You can plug that in. And then we can multiply these in any order. It's just a multiplication problem at this point, with 4 different things being multiplied. 5 squared, 25, 12, 1/3. So 1/3 of 12 is 4. 4 times 5 squared, which would be 4 times 25, is 100. So you'd have 100 pi on this one. You could get to that, I think, without a calculator, but feel free to use the calculator if need be. And I was going to write centimeters, but it's meters here. So meters cubed, this would be an exact answer. You could plug this in to a calculator. If you know pi to at least 4 digits, you could get this without a calculator, 3.14159.265, and so on. So we round that off. 314, we're multiplying by 100, so moving the decimal place 2 spots. 0.2 rounded off meters cubed. On this one, formula is going to be the same. This is going to be my h here, so it looks like this. We're assuming that's a 90-degree measure there. And then this would be 30 degrees, so you have a 30, 60, 90 triangle right here. So hopefully you remember your ratios for those. The short leg should have been the n part, or the 1 part. This was the n root 3 part right here, square root of 3 part, and then the hypotenuse is 2n for that. So if I know that 2n equals 14, if I divide by 2, that means n would equal 7. And n is also the equivalent to the radius in this case. So this means the radius is 7, and then the height is n root 3. So just plug in 7 and you have 7 root 3. So now we have everything we need for the formula. My formula is 1/3 pi r squared h. It's really just base times height, 1/3 base times height rather. And so I've got 1/3 times pi times 7 squared times 7 root 3. So I've got 1/3 of, and this would be 49 times 7, 243. And so for that leaves me, or that's 243, 343, sorry. So I've got 343, and that divided by 3, it doesn't work out nice. So if you were to leave this exact, it would be 343 times the square root of 3. And there's a better way I should write this. So before the square root of 3, I want to write the pi, so it doesn't look like the pi is under the square root potentially. So 343 pi, that's 7 squared times 7, 343, times pi, times the square root of 3. All that divided by 3 would be the same as multiplying it by 1/3. So this would be an exact answer, and it would be meters cubed. Plug that into a calculator, and you could get this approximate answer, 622.1 meters cubed. And from there, let's take a look at some pyramids to wrap up this lesson. So on this one, we are looking at here is the height. I gave you the slant height on this one. So this is what I'd call cursive L. This is 28 all the way across. We're assuming this is a not an oblique or a slanted pyramid, but it's just straight up and down. We call that a right pyramid. We've got 28 here. That would make this 14 right here. We're just dividing by 2, splitting that in half, being directly aligned with the center up to the apex or the vertex of the pyramid there. So you've got 14 squared plus h squared would equal 50 squared on this one. So 14 squared plus h squared, let's do that work to get what h is, equals 50 squared. Remember, for my formula, I'm going to be using this 1/3 area of the base times the height. So I need the height. I need this part. And then the area of the base, it's just you can assume a square pyramid since there's no other information given to you here. Assume these are both regular polygons for the bases. So it's just going to be 28 times 28. A square, just a special type of rectangle, just base times height. So we have, for this one, going back to the Pythagorean theorem work, 196 plus h squared equals 2,500. Subtract 196 from both sides, and you are left with 2,304. You can take the square root of both sides from there and get that h is 48 from there. So that ends up working out nicely. It is 14, 48, 50 as a Pythagorean triple here in this one. So I'm going to take that, plug it in down here. Got 1/3, and then 28 times itself, base times height of the base, and then that times 48. And you could use a calculator here to assist you on this one. It looks like we've got 12,544 centimeters cubed for this particular problem. And then finally on this one, we are assuming this is a regular polygon. This triangle right here is what I'd want to focus on. And I'm going to be looking at that's not the best drawing I could have there. I was pretty happy with how the triangle came out, but assume right there, that's your triangle that you're going to try to figure out the area of and multiply that by 6, because you could have 6 of those same triangles. So this shape I'm going to make a little bigger right here, this blue triangle. Ugh. Sometimes it is hard to freehand with this tool here. There we go. So decent, could do better with that picture, but good enough for what we're trying to do here. This would be the apothem if you're familiar with that language or remember that language, but if you can just think of this as the height of this little triangle, that's fine as well. So you could call that A, or you could call that H. A for apothem, H for the height of this triangle. B is going to be the base of this whole triangle, and then I'm going to call this x, this would also be x in that case then. So we know that b is 8, so I'm going to replace b with 8. I'm told that information here. I feel like I did not do a good job of giving you the big picture of this. Where are we going with all this? The volume of this is 1/3 BH. So I know that H is right here, the height, this H is the height of the pyramid, it's 12. But I need to figure out the area of the base. So I don't have that information yet. The base is this hexagon. I'm going to be figuring out the area of this triangle and multiplying it by 6 to get there. So I've got x would be 4 if 8 is all the way across. Each one of these is 4 and 4, and then you could figure out this angle from there. So if you do this the way I had taught in the previous chapter, we're thinking 360 divided by 6 would get this whole angle, because we've got 6 of these same size or congruent triangles. Then we would split that in half, divided by 2. So hexagons, which is what this base is of the pyramid, they always end up working out as a 30, 60, 90 triangle. I need to see that you understand that, though. If I was checking for work, I would want to see that. So 30 degrees there, 60 there. We could use trig for this then, but I think more easily or more efficiently we could use the ratios of a 30, 60, 90 triangle. So this is n, this is 2n, and then your apothem or height of that triangle is n√3. So n is 4. That means the height of this triangle right here, or the apothem, if you prefer to think of it that way, would be 4√3, since n is 4. So then I could take this, I've got 1/3, and then you could write 1/2 perimeter times apothem if you prefer it that way, or you could write the area of one triangle. This is the way I had taught it, at least in the YouTube video for that lesson that I made. I think that was 10.4. Part 2, but don't quote me on that. But it's the area of one triangle of the polygon's base times the number of triangles you could make. And then that times the height of the pyramid itself. So this one, I know the height of the pyramid, so why don't I replace h with 12 right there in this step. And I could say this would be 1/3 times 1/2 base times height of the triangle times the number of triangles that I could make like that, which would be 6. So now I've got 1/3 times 1/2. The base of that blue triangle is 8. So I'm going to replace this b with 8. That's the base of the triangle portion of that. And then the height of that triangle was the same as the apothem here, 4√3. So now I have all the numbers, all the values plugged into the formula, and I just need to figure out that. And hold the phone. Where'd my 6 go? Don't forget my 6. There we go. So that times 6, because there's 6 of those triangles you can make. So we have that, and then we got that all multiplied together. Well, let's see if I can do this in my head just for fun. So this would be 30, no, this would be the easiest way to do this. 1/3 times 1/2 would be 1/6. 1/6 of 6 is 1, so that kind of all goes away. And then 8 times 4 is 32, and 32 times 12 looks like is 384. I got that right. 32 times 12, yeah. So that would be that times the square root of 3. This would be an exact answer. Units were given in yards, so you could say YD or YDS cubed, and round it off to the nearest tenth, 665.1 yards cubed. So that does it for this lesson. Hope you found that helpful. The next lesson we'll be looking at spheres, which is a three-dimensional object we haven't talked about at all yet. With this new textbooks version, we do all pyramids, cones, prisms, and cylinders before talking about spheres at all. So the next lesson, we'll look at spheres. But again, Google that if you want to know how that formula is derived. You may need a little more mathematical background before you're ready to fully understand the proof of that, but it's a pretty cool one. I hope you found the lesson useful or the notes useful, and hope you have a great day. Bye-bye.